Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 20th, 2026, just yesterday. It addresses the often overlooked challenge of efficiency in large language model agents, proposing a comprehensive taxonomy to optimize memory, tool use, and planning for real-world deployment. The paper is titled, Toward Efficient Agents, Memory, Tool Learning, and Planning. And as we'll see later, the discussion on balancing performance against cost offers some really valuable insights for anyone building production systems. For those interested in the implementation, the authors have shared their code on GitHub. To get us started, Figure 1 visualizes the research landscape as a growing evolutionary tree. It splits the field into 4 distinct branches: efficient memory in blue, tool learning in green, planning in purple, and benchmarks in orange. The vertical timeline shows how the field has exploded from foundational models in 2023 up to the diverse ecosystem of 2025. This taxonomy really sets the stage for the specific techniques the authors analyze next. So Figure 2 conceptualizes the shift from a standalone model to a full agentic system. At the center sits the pure LLM, representing isolated reasoning. Surrounding it are the 3 pillars that define an agent: memory at the top, tool learning on the left, and planning on the right. Notice the arrows radiating outward, each marked with a $sign. This highlights a critical trade-off. While these components extend capabilities, they inevitably introduce new costs like latency and API fees. Alright, Figure 3 breaks down the lifecycle of efficient memory into 3 distinct phases. First, the blue section on the top left illustrates memory construction, which organizes raw context into working or external memory to handle token limits. Next, the green panel on the top right covers memory management. Here, a manager, often large language model based, actively curates the data by adding or deleting items to keep latency low. Finally, the bottom pink section details memory access, showing how the system retrieves memories and integrates them, for instance by injecting latent representations, the model's internal numeric states, rather than reprocessing full text. Next, Figure 4 maps out the second major pillar: efficient tool learning. The diagram divides this process into 3 stages, flowing from left to right. On the left, the tool selection phase filters the vast ocean of potential APIs, sometimes even treating tools as special vocabulary tokens to speed up retrieval. In the middle, the tool calling panel focuses on execution mechanics, such as running tools in parallel or using budget constraints to limit expensive calls. Finally, the purple section on the right details tool integrated reasoning, which uses policy optimization to shorten the reasoning path and avoid unnecessary steps. Figure 5 outlines the third pillar: efficient planning. The header illustrates the central tension, balancing the scale between maximizing task success and minimizing costs. On the left, panel A details single-agent strategies, where the agent backbone uses budgeted deliberation to dynamically adjust reasoning depth based on strict token and latency budgets. Switching to the right, Panel B focuses on multi-agent efficiency. It highlights topological efficiency, which replaces chaotic, dense communication webs with sparse, structured connections to reduce unnecessary chatter. So wrapping up, the central message here is that future research must prioritize deployment costs just as much as raw capability. We need to optimize memory, tools, and planning to ensure agents are not only smart, but also economically viable in the real world. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.